Hi everyone, I am Madhusudan. Presently I am working as assistant professor in the Department of Physics at ATME College of Engineering myself. Welcome you all to this talk. Today we will be discussing about nanomaterials and nanotechnology, what exactly this nanomaterials mean. When did this nanotechnology came into existence into India? Like when did we start research? Like whether this is a nanotechnology and nanomaterials or nanoscience and nanotechnology, what is the difference between this nanoscience and nanotechnology? What exactly this nano means? Nano is a very buzzing word in the present scenario, and probably this has its applications almost in all the fields of science and engineering. And this nanoscience simply means that every day is a new day for a researcher, because the happenings, the findings, the research what we do is entirely new, and probably you are all aware that majority of the inventions and discoveries, everything was by accident, and probably for a researcher like we should be very keen in the observation. If you are very keen in observation, then we can exactly probe what is the difference, what is the change which has been observed, and therefore the observation is the key point for any researcher in the science and technology field. And therefore this nanoscience, this will lead to new areas of research, probably in all the branch of science and engineering. You take any branch for that matter, you name any branch for that matter, probably this nanomaterials and nanotechnology has almost all the applications in all the branches of science and engineering. What exactly we do in this nanoscience? We scale down to the nanometer regime, and then we go for the better understanding of the matter and their interactions, so that majority of the properties are being led, whether it is chemical properties, physical properties, you name any properties, electrical properties. So all these properties are being changed when you compare your material with respect to bulk and with respect to nano. You have lots of changes, and that is the reason everywhere people say nano, nano, everywhere nano, and therefore majority of the researchers are into the nano research. So this nanomaterials or nanotechnology, if you take into consideration, this is a new way to tackle important problems in science. So this simply means that by learning about an individual atom or molecule's properties, we can put them together in very well defined ways to generate new properties with new and amazing characteristics. So the plan of the talk, initially like what I'll do, I'll go with the introduction. So I'll give a brief outline on the introduction about the nanomaterials. What are the different properties of these nanomaterials? What is the difference between the bulk material and when we scale down to nano regime? And very importantly, we'll see the main thing is size of the size dependent properties, which means to say we have n number of properties which is going to change, and therefore this nano has gained importance only because of this, and therefore size is very important. Whenever you say we have synthesized some nanomaterial, we have to immediately tell what is the size of the nanoparticle which we have synthesized. Similarly, the next thing is synthesis of nanomaterials. So synthesis is very important for any of the research to carry out or to proceed. Synthesis is very important, which we call it as, in technical terms, we call it as a precursor. So initial material is very important, and in this synthesis we have different types of synthesis, wherein I go for physical synthesis, and I have chemical synthesis, and next I have biological methods of synthesis. And therefore these are all the three types of three methods by which we can synthesize nanomaterials: physical methods, by chemical methods, by biological methods, and we also have what is called as hybrid method. What is this hybrid method? It is a combination of any of these two, a combination of a physical and chemical, or a combination of physical and biological can give rise to the hybrid methods of synthesis. And then I'll be discussing about the nanoscale materials, nanoscale materials, one of it, the majorly discussed material is CNT. We call it as carbon nanotubes, and we in simple terms we call it as CNT. And the next thing is characterization. Characterization is very important. Why this characterization is important? Characterization is very important because we have to very exactly probe what is the size of the material, or we have to determine what are the properties of the material, and under this characterization we have n number of techniques. We have highly sophisticated instruments like XRD, X-ray diffractometer, SEM, scanning electron microscopy, and TEM, transmission electron microscopy. Similarly, we have n number of characterization techniques. We have UV visible spectrometer, we have FTIR, etc. We have IDAX, and we have so many characterization techniques. And ultimately, when I come to know, when I determine what are the properties, then I go for the application part. So this is where the exact work of an engineer or a technologist lie. Whenever we have understood the properties, I have characterized what is the size of the material, what is the nature, whether it is a nano flower, whether it is in the form of a nano rod, I can very exactly go for the application part of it. And this is very important. It is not just only we say like taking a scanning electron microscope image and we say this is so much nanometer, the size of the material is so much nanometer, but ultimately when we give the application part, when we go in the product level, which is very important. And when we jump into this nanomaterials and nanotechnology, as we have father of the subject for each and every subject, we have a father of nanotechnology who is Richard Feynman. Probably you are all aware that Richard Feynman, he was one of the fantastic physicists, and therefore in his talk in 1959 at Caltech University, it was for the first time that he uttered the words nanotechnology. So that was really altogether a new word. What is this nanotechnology? And from there he started and he uttered these lines, like he said, there is plenty of room at the bottom. So what does this simply mean? There is plenty of room at the bottom. What do you exactly mean by bottom? Which means to say that we have a material in the bulk form. For example, I have a chalk piece. This I consider it as a bulk form, as I can see it through my naked eyes without any sophisticated instrumentation to probe, to visualize this. And therefore, this I can see through my naked eyes, and therefore if I scale down, if I chop this to n number of times, probably it becomes very minute, and ultimately at some point of time it reaches some nanometer, and therefore I can say if the dimension along, if the size of this material along any one dimension, let it be x-axis, y-axis, z-axis, if it is less than 100 nanometers, then we say this is in the nano regime. So this is simply termed as nanometers, and it is designated by small n and small m. This n refers to nano. Nano simply means it is 10 raised to power 9, and this we know very well, meter is the unit to determine any physical quantity, related physical quantity. And we have one more person who is Eric Drexler. He is the author of Nanosystems and Molecular Machinery, Manufacturing and Computation, and he has also contributed to this nanomaterials and nanotechnology as to how exactly these nanosystems work. And therefore, going back to the history of nanotechnology, I already told that on 29th December 1959 at the annual meeting of the American Physical Society at California Institute of Technology, this Richard Feynman, he uttered the words, there is plenty of room at the bottom, and therefore we regard him as the father of nanotechnology, because he was the person who told how to zoom in, how to chop the materials, a bulk material which you can see through your naked eyes, chop it into n number of structures, go to the level of nanometers, and therefore when you come to this size which is nanometers, you can come across different properties which are being changed. What are the properties which are being changed? The properties may be with respect to physical properties, with respect to chemical properties, with respect to color change, with respect to conductivity, there are with respect to magnetic properties. So there are n number of changes which are being observed, and this is the difference between a bulk material and scaling down to nanomaterial. And therefore, what exactly is this nano? Nano simply means that it is 1 billionth of something. So 1 billionth, you can simply imagine, it is so small that if I take this chalk piece and if I chop it into 1 billion times, the smallest thing what you can get is nanometer. And there, at this small scale, at this regime, we are exactly jumping in now. And therefore, what is this nano? Nano is nothing but 1 billionth of something. And therefore, as I told, this we can go into, this we can study. So we can divide this into nanoscience and nanotechnology. But as you are all aware that we need no discrimination, because without science there can be no technology, and without technology probably science does not exist. And that is the reason if we say nanoscience and nanotechnology, both are merged together and it goes hand in hand. And therefore we also know that science, the basic science people or the scientists, what they do, they generate, they understand the basic mechanism, they understand the basic logic, and they define it in a very clear way. And what these technologists do or engineers do, they simply take this, they understand the mechanism, they understand the logic, they take this forward and bring it in the form of a product. And that is why I told, like, both science and technology should go hand in hand. And therefore science people, they give the mechanism, the understanding they are going to provide, and this technology people, they take that logic and they are going to bring it in the form of a product, and they are going to address the day-to-day problems. And for our convenience, probably you are all aware, you have come across all these scales. We generally represent any dimension, any physical quantity by meter, or suppose if we go much more smaller, we say it is millimeter, which means to say it is 10 power minus 3 meters. And further moving down, we have micrometer. Micro is simply 10 power minus 6, and further if we go, we come across this nanometer, and it is 10 power minus 9 meter. And this is where exactly we are going to deal with, and in all the further coming further talk, I am going to discuss about the change in the properties when we scale down our matter to this nanometer regime. Further we have scales which is called as picometer, which is nothing but 10 power minus 12 meters. Further we have femtometer, which is 10 power minus 15 meters. So what are these nanoscale measurements? These nanoscale measurements, this is just an approximation for us. For example, if I take a tennis ball, and this tennis ball is very exactly, I can visualize through my naked eyes, and I don't require any additional instrumentation to probe it, and therefore I can visualize my tennis ball directly through my naked eye. Further, if I scale down and go to a cancerous cell, if I go to visualize a bacteria, if I go to visualize a virus, then antibody, then probably all these are nothing but I am scaling down, which means to say if I decrease the size, probably with respect to the size, I require additional instrumentation, I require sophisticated instruments to probe that smaller objects. And we have in the devices, for example, if we come across to this nano devices, we come across nanopores, we come across dendrimers, we have nanotubes, we have quantum dots, we have nanoshells, etc., etc. And all these nano devices can be probed by the utilization of this sophisticated instrumentation. So with all these basics, with all this introduction, what does a nano simply mean? Nano is derived from a Greek word which means nanos, which means to say its meaning is dwarf, or it is very small. So as I told, if we take one particle, or if I say nano, it is nothing but 1 billionth of something. Even if I take a single strand of hair and if I chop it to 1 billionth time with respect to size, then that smaller size whatever you get is nothing but our nanometer. And therefore simply this nanometer is nothing but 10 power minus 9 meters. So this is the scale where we are dealing with. So similarly, we can also have the observation, what we observe. For example, I have, through my naked eyes, I can visualize a cat which is moving around, I can visualize a dog, and further, if I want to see some distant objects, for example, if I want to see a particular star, if I want to visualize a planet, then it is very obvious that my eye has certain limitation, and my eye is not the suitable equipment to probe very farther object. So if I want to probe anything with respect in galaxy, or if I want to probe any let me say planet, it is my eye is not the suitable equipment to probe it, and in situ, like, we require the necessary instrumentation to probe that. Further, on the other hand, if I scale down, if I go to very smaller objects, an atom and DNA, nucleus, so if I go with respect to reduction in the size, even then I require sophisticated instruments where I can exactly probe the smaller objects also. So the eye, what we have, has certain limitation, and it is restricted to a particular size. Even if I reduce my size, I want sophisticated instrumentation, and even if I increase my size, I require suitable observation, suitable instrumentation also. Therefore, with respect to this size, as we discussed, with respect to this size, we require sophisticated instrumentation. So when we come back to this nanoparticles or nanomaterials, how can we define them? For example, if I say, if I want to tell like any of the material, it is in the nano regime, then the size of it along any one dimension should be from 1 to 100 nanometers. If the size is from 1 to 100 nanometers, then I can say this is a nanomaterial, or I can say that it is a nanoparticle. And probably you are all aware that when something comes for the first time, or if it is new, probably people were working around 1 to 100 nanometers, and it was around I think it was in 1980s when this nanomaterials, nanoparticles came into India, and even the Indian researchers started to probe this for the synthesis, fabrication. Then this was the scale. But now we have progressed a lot, and therefore if I want to say nanometer, then if I have the scale between 1 to 10 nanometers, then we say this is ultra fine particles. And probably now if I say I have synthesized some 80 nanometer particle, then probably people won't be much excited. At the same time, if I say I have synthesized some 8 nanometer particle, 2 nanometer particle, then it is obvious that people focus that what he has synthesized. And therefore, these nanoparticles may or may not exhibit size related properties that differ significantly from particle to particle, and it also depends on the process what we have employed, and therefore this difference between the bulk material and the nanomaterial is what is going to make the change, and that is why this nanotechnology is in the market. So this has gained lot of interest in the present days, and therefore this nanometer, and that too even if we speak of this ultra fine nanoparticles, that means where its size lies between 1 to 10 nanometers, people are really interested. And this nanoparticle research is the current area of intense research interest due to a wide variety of potential applications in almost all the fields of science and engineering. You name any field, civil, mechanical, electrical, electronics, basic sciences, physics, chemistry, where not, like everywhere this nanomaterials has applications, and this nanomaterial is in high demand in the market. And we have classification of this nanomaterials. So as we reduce the size along the coordinates, we have the dimensions. For example, if I take 3 dimensions, then if we can term it to be a nanoparticle or quantum dots. By the definition itself, as I told, if it is from 1 to 100 nanometers, we say it is a nanoparticle, and to be very specific, we say it is a quantum dot. Suppose if I have 2 dimension, so 2 dimension along x and y axis, then I term it to be nanotubes, or it may be nanowires, or it may be nanofibers. It will be in the structure somewhat like this. So it is a 2-dimensional structure, and therefore we can term it to be this. Suppose if I want to go for a film, and it will be one dimension, and this can be, it can be simply any of the coatings, or I simply call it as thin films. So if I take any substrate material, if I want to coat it, then that is nothing but a thin film, and if we deposit coatings on any substrate material, probably that would be along one dimension. So now let's proceed about how these properties are going to change with respect to the reduction in size. Smaller size means larger surface area. For example, if we consider a sphere, the particle size, the particle shape, suppose if we consider in the form of a sphere, then we are very much interested in determining S by V ratio. What is this S by V ratio? S simply means that it is surface area, V simply means that it is the volume of the sphere. And we have surface area, which is given by surface area S equals 4 pi r square. And if I take into consideration this volume, V is equal to 4 by 3 pi r cube, where r is the radius. And suppose if I take this S by V ratio, what is this S by V ratio? S divided by V, 4 pi r square divided by 4 by 3 pi r cube. So this S by V ratio turns out to be S by V equals 3 divided by r. Or we know that 3 is a constant, it is a number, and therefore I can also write it as S by V is proportional to 1 by r. Or I can say S by V is inversely proportional to the radius. So what does this mean? This simply means that as I decrease the radius of any material, if I have taken this much size particle, so I am reducing the size, then what is going to happen? If I am going to decrease the radius, my S by V ratio is increasing, that is surface to volume ratio is being increased. Suppose if I am decreasing this, the area of interaction whichever is available is going to increase as I decrease my radius. So I'll take an example. Let me take a radius along one column, S by V along another column. For example, let me assume radius is 3. So what is my S by V ratio? Then this is nothing but 3, radius is 3. So here 3 divided by 3, this is simply 1. So I am going to reduce further. So the radius, suppose if I am taking it to be 2, I am taking it to be the radius to be 2. Then what is going to happen? This S by V ratio turns out to be 1.5. And further if I am decreasing, if my radius is 1 and this turns out to be simply 3. So the radius is 1, therefore radius is 1, 3 divided by 1 is 3. So further if I keep on reducing, if I take it to be 0.5, then this turns out to be 6 S by V ratio. If my radius is 0.25, this turns out to be 12, and if my radius is 0.125, further I am reducing and this turns out to be 24. So have you observed this pattern? Which simply means that as I am decreasing the size, of the particle, my surface to volume ratio is increasing. This simply means to say that the area of interaction which is available is going to enhance by so many folds, and therefore this is the main key point where this bulk material, when you compare with nano material, has n number of changes in the properties. As I told, the properties may be anything. It may be with respect to physical, chemical, with respect to color change, it may be anything. And therefore this is the point, this is the key point. When we decrease the radius of any material, when we decrease the radius of any particle, my surface to volume ratio is going to increase. So as I told, the properties of nanoparticles are going to change. How is it going to change? What are the different properties? These nanostructures or nanomaterials exhibit properties different from their macro scale counterparts. As I told, when it was in the form of a bulk matter, and if you reduce it to the nanometer regime, it is going to change its properties. What are these properties which are going to change? The first thing is we can go for the mechanical field, which means to say the mechanical strength is going to increase. That means, what is this mechanical strength? How hard they are to break, and therefore when you scale down to this nanoparticles or this nanometer regime, it is very obvious that it can increase the mechanical strength of the material. Similarly, if we go for electrical conductivity, so what do you mean by this conductivity? How fast it can flow, right? And therefore how fast these electrons can flow through the material is going to determine what this electrical conductivity is. And next thing is thermal conductivity. So thermal means we know it is heat energy, how it can simply move, and therefore how fast this heat can flow through a material. So that is attributed to the thermal conductivity. And also the chemical reactivity, how fast they react with the chemicals. Yeah, so how fast it can proceed with a chemical reaction. And we are all aware that when you take a bulk material and when you take a very small material of the order of some nanometers, it is very obvious that there is a dissolution rate is going to be faster in the case of the smaller particle size. And even the next point is, if you go to transparency, few of the materials in the bulk form may be very much opaque, where you cannot see from one point to another, whereas if you go for this nanometer regime, it becomes transparent, which means to say you can see from one point to another point across, you can see along that material. And next thing is magnetism. So whether they are magnetic or non-magnetic, we can also determine. So these are all the properties, and there are many more where these properties are going to change when you come across these nanoparticles. That means when you scale down from the bulk matter to the nanomaterials or nanoparticles. These optical properties of nanomaterials can be significantly different from bulk materials, which means to say the metallic nanoparticles, they change the color in spectra. For example, if I have seen certain material in the bulk form, if it is in green color, and if I scale down the same material to the nano regime, probably that would be yellowish in color. So the optical properties also change. The next point is with respect to electrical conductivity. This electrical conductivity decreases with a reduced dimension due to increased surface scattering. As I told you, as we decrease the size, the surface to volume ratio is going to increase, and therefore this electrical conductivity also increases due to the better ordering and ballistic transport. And these nanomaterials, they are also used for self-purification. The self-purification is an intrinsic thermodynamic property of nanostructures and nanomaterials due to enhanced diffusion of impurities or defects or dislocations to the nearby surface. So with all these properties, we can say that most are tunable with respect to size, and that is the reason I told you in my initial slides that when you say that I have synthesized certain nanomaterial or certain nanoparticles, immediately you have to say what is the size. So that becomes very important.